the elements oxygen, sulfur, selenium, tellurium and polonium constitute the 16th vertical column or 6A group elements in the long form of the periodic table. The first 4 elements of the group are collectively called chalcogens or ore-forming elements. Because a large number of metal ores are found in the Earth's crust as oxides or sulfides. Oxygen is the most abundant element available in nature. It forms 20.946% of air by volume and 46.6% of the Earth's mass, mostly in the form of silicates and other compounds like carbonates, sulfates and oxides. Most of the oxygen in the atmosphere is produced by photosynthesis in plants. It also occurs in the form of ozone, which is an allotrope of oxygen in the upper atmosphere, and protects us from the harmful radiations of the sun. Sulfur is the 16th most abundant element and constitutes about 0.034% by weight of the Earth's crust. In its combined form, sulfur is found in ores in the form of sulfates and sulfides. Sulfates include gypsum, CaSO4, 2H2O, Epsom salt, MgSO4, 7H2O, and barite, BaSO4. Sulfides include zinc blende, ZnS, galena, PbS, and copper pyrites, CuFeS2. Sulfur is also present in organic substances like mustard seeds, eggs, onion, garlic, wool, and hair. Sulfur is available in its free state in the volcanic areas of Sicily, Italy, Japan, America, Russia, and Iceland. Small deposits of sulfur are found in Pakistan and India as well. Natural gas and crude oil are other sources of sulfur. Selenium and tellurium are present in sulfide ores as metal selenites and tellurites. Polonium is a radioactive element with a half-life of 13.8 days and is very rare. It occurs in nature as a decay product of uranium and thorium minerals. Look at the electronic configuration of these elements. All the elements of this group have 6 electrons in their outer shell and have the general electronic configuration of Ns2Np4. Now, let's look at the atomic and physical properties and their trends in these elements. Let's begin with the atomic and ionic radii of these elements. From the given electronic configuration, we observe that due to the addition of a new principal energy level in each element, the atomic and ionic radii increase from oxygen to polonium. As you can see from the table, oxygen has an exceptionally small size. This is due to the higher effective nuclear charge of the oxygen atom. You already know that as we move down a group, ionization enthalpy decreases with an increase in the size of the atom. In group 16 elements too, the ionization enthalpy decreases with an increase in the size of the atom from oxygen to polonium. However, note that the elements of this group have lower values of ionization enthalpy than that of group 15 elements. This is because group 15 elements have a stable half-filled p subshell in their valence shell. Due to the extra stability of their half-filled configuration, more energy is required to remove electrons compared to group 16 elements. Let's now see the electron gain enthalpy of these elements. In general, down a group, electron gain enthalpy decreases with an increase in the size of the atom. Thus, the electron gain enthalpy of group 16 elements decreases with an increase in the size of the atom from oxygen to polonium. However, note that the oxygen atom has a less negative electron gain enthalpy than sulfur. This is because oxygen, due to its compact nature, experiences more repulsion between the electrons already present and the incoming electron. Due to these electron-electron repulsions, an oxygen atom has lesser tendency than a sulfur atom to accept the extra electron. Let's look at the trend in electronegativity. As we move down the group from oxygen to polonium, the electronegativity decreases gradually with an increase in the atomic size. Note that oxygen is the second most electronegative atom after fluorine. Let's now learn about the physical properties of the group 16 elements. Oxygen and sulfur are nonmetals. Selenium and tellurium are metalloids, while polonium is a metal under normal conditions. As polonium is a radioactive element, its radioactive property is considered more important than its normal properties. Moreover, its availability is very less as it is a decay product of uranium and thorium. All the elements of group 16 exhibit allotropy. Oxygen has two allotropes, which are oxygen and ozone. Although sulfur has many allotropic forms, only two of them are stable, which are rhombic and monoclinic. Selenium and tellurium exist in both amorphous and crystalline forms. The melting and boiling points of the elements of group 16 increase from oxygen to tellurium as their atomic size increases. This is because, as their atomic size increases, the van der Waals force of attraction between the atoms increases. However, the large difference between the melting and boiling points of oxygen and sulfur may be explained by the fact that oxygen exists as a diatomic molecule, while sulfur exists as a polyatomic molecule. First, let's take a look at the oxidation states of the elements of group 16. As all the elements of this group have a configuration of Ns2np4 in their valence shell, they may attain noble gas configuration either by gaining 2 electrons, forming M2- ions, or by sharing 2 electrons, thus forming 2 covalent bonds. Hence, these elements show both negative and positive oxidation states. The table here gives details of the different oxidation states shown by these elements. The electronegativity of oxygen is very high, second only to fluorine. Therefore, it exhibits a negative oxidation state of -2 in all its metal oxides. Thus, most metal oxides are ionic and contain oxide ions. In addition to -2 oxidation state, oxygen shows -1 oxidation state in peroxides. Since the electronegativities of the elements decrease as we move down the group, the tendency of these elements to show -2 oxidation state decreases from sulfur to polonium. Since polonium has the least electronegativity, it does not show an oxidation state of -2. Instead, it shows only positive oxidation states. Talking about positive oxidation states, oxygen shows positive oxidation state only in its compounds with fluorine, since fluorine is the only element more electronegative than oxygen. It shows +2 oxidation state in oxygen difluoride and +1 in dioxygen difluoride. Note that oxygen does not have d orbitals, and therefore it cannot expand its valency. Hence, the oxygen atom cannot show an oxidation state higher than +2. The other elements of the group, apart from exhibiting +2 oxidation state, also exhibit +4 and +6 oxidation states due to the availability of d orbitals in their atoms. These elements show +4 oxidation state in their compounds with oxygen and +6 oxidation state with fluorine. Due to the inert pair effect, the stability of +6 oxidation state decreases, while the stability of +4 oxidation state increases down the group. Oxygen, like the other p-block elements present in the second period, differs considerably from the rest of the elements in its group. These differences are due to its small size and high electronegativity, and the absence of d orbitals in the valence shell of the atom. The important differences are atomicity, oxygen is diatomic and gaseous, while the other elements have complex structures and hence exist as solids. Formation of N2- ions. Oxygen, due to its high electronegativity, shows negative oxidation state and does not show any positive oxidation state except in oxygen difluoride and dioxygen difluoride. The other elements show +2, +4 and +6 oxidation states in addition to -2 oxidation state. Polonium does not show minus oxidation state. Maximum covalency. Due to the absence of d orbitals in oxygen, its covalency is limited to 2. But the covalency exceeds 4 in the other elements due to the availability of d orbitals in them. Hydrogen bond formation. Because of its small size and high electronegativity, oxygen forms strong hydrogen bonds, which greatly affects the properties of water and other compounds. However, the other elements in the group have comparatively low electronegativities and, therefore, do not form hydrogen bonds. Now, let's discuss the chemical properties of these elements. The elements of this group react with hydrogen to form hydrides of the type H2E, where E could be oxygen, sulfur, selenium, tellurium, or polonium. The physical states, melting points, boiling points, enthalpy of formation, enthalpy of dissociation, and dissociation constants of these hydrides are given in the table here. Let's look at the physical states of these hydrides. Water is a colorless and odorless liquid, while the hydrides of all the other elements of the group are colorless, poisonous gases with unpleasant odors. The boiling point of the hydrides markedly decreases from water to hydrogen sulfide and then increases. Water has an abnormally high boiling point because its molecules are associated with each other by means of hydrogen bonds in its solid as well as liquid states. On moving down the group, the boiling point increases from hydrogen sulfide to hydrogen telluride because of the increase in molecular weight. The thermal stability of these hydrides decreases with a decrease in the bond dissociation enthalpy of the He bond from H2O to H2Te. As can be seen from the dissociation constant values, the acidic character of the hydrides increases from H2O to H2Te. The increase in acidic character is due to the decrease in the He bond dissociation enthalpy from H2O to H2Te. Except for water, all the other hydrides act as reducing agents. The reducing property of these hydrides increases from H2S to H2Te. This is again due to the decrease in their thermal stability from H2S to H2Te. All the elements of this group react with oxygen to form dioxides and trioxides of the type EO2 and EO3 respectively, where E could be sulfur, selenium, tellurium, or polonium. Both these types of oxides are acidic in nature. Ozone, which is treated as a dioxide of oxygen, and sulfur dioxide are gases, while selenium dioxide and tellurium dioxide are solids. The reducing property of these dioxides decreases from sulfur dioxide to tellurium dioxide. Sulfur dioxide is a reducing agent, whereas tellurium dioxide is a good oxidizing agent. Sulfur trioxide is the only important triode in this group. At room temperature, sulfur trioxide is a solid and exists in three distinct forms: alpha, beta, and gamma. Group 16 elements form a large number of halides of the type EX6, EX4, and EX2, where E is a group 16 element and X is a halogen. Among hexaldehydes, only hexafluorides are stable. They are all colorless gases. They undergo sp3d2 hybridization and hence have octahedral geometry. Sulfur hexafluoride is an extremely inert, colorless, odorless, and non-flammable gas and is insoluble in water. Among the tetrafluorides of group 16 elements, sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride a solid. These tetrafluorides undergo sp3d hybridization and hence have trigonal bipyramidal geometry, in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also known as seesaw geometry. Except for selenium, all the other elements of this group form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral geometry. The presence of a lone pair of electrons gives it a bent geometry similar to that of water. Monohalides exist as E2X2 and are dimeric in nature. Monohalides undergo disproportionation and are converted into tetrahalides. For example, selenium monochloride disproportionation to form selenium tetrachloride and selenium. The structure of these monohalides is similar to that of hydrogen peroxide with a bond angle of 104 degrees. Dioxygen is prepared by different methods in the laboratory and commercially. Let us first study the laboratory methods. The most convenient method for preparing dioxygen in the laboratory involves the catalytic decomposition of solid potassium chlorate. Manganese dioxide is used as the catalyst in this reaction. The other laboratory method is the thermal decomposition of oxides of metals from the lower part of the electrochemical series. For example, the thermal decomposition of silver oxide or mercuric oxide gives dioxygen. Dioxygen may also be obtained in the laboratory by heating the higher oxides of some metals like lead, barium, and manganese. The thermal decomposition of salts rich in oxygen, such as nitrates, for example, potassium nitrate or sodium nitrate, and permanganates, for example, potassium permanganate, also yields dioxygen. Commercially, dioxygen is prepared by either the fractional distillation of liquid air or by the electrolysis of water. To prepare dioxygen from air free from water and carbon dioxide is first liquefied. The remaining constituents of liquid air, primarily liquid oxygen and liquid nitrogen, are separated by means of fractional distillation. The electrolysis of water containing a small amount of sulfuric acid or barium hydroxide leads to the liberation of oxygen at the anode and hydrogen at the cathode. Now, let's discuss the properties of dioxygen. Dioxygen is a colorless, tasteless, and odorless gas. It is slightly heavier than air. It is slightly soluble in water to the extent of 3.08 cubic centimeters in 100 cubic centimeters of water at 293 Kelvin. This small quantity of dissolved dioxygen is just sufficient to support marine and aquatic life. It can be liquefied under pressure to a pale blue liquid by compressing the gas at 90 Kelvin. It can also be solidified into a bluish-white solid at 55 Kelvin. It has three isotopes forms with mass numbers 16, 17, and 18. In spite of having an even number of electrons, dioxygen exhibits paramagnetic behavior. This property can be clearly explained by the molecular orbital structure of the dioxygen molecule. Let's now see the chemical properties of dioxygen. Dioxygen is a very reactive element and reacts directly with nearly all metals and non-metals. However, it does not react directly with some metals like gold and platinum, and some noble gases like helium, neon, and argon. In spite of the great reactivity of dioxygen, some external heating is required to initiate the reaction, as the bond dissociation enthalpy of the oxygen-oxygen double bond is very high. However, as the reactions are highly exothermic, once started, they proceed rapidly without further application of heat. Let's see the reaction of dioxygen with metals. Most metals burn in dioxygen and form oxides that are mostly basic in nature. The reactions of dioxygen with metals such as calcium and sodium are shown here. Similarly, most non-metals burn in dioxygen to form acidic oxides. The reactions of dioxygen with sulfur, carbon and phosphorus are illustrated here. Let's look at the reactions of dioxygen with some compounds. Sulfur dioxide undergoes catalytic oxidation in the presence of vanadium pentoxide to form sulfur trioxide. This is an important step in the manufacture of sulfuric acid by the contact process. Similarly, hydrochloric acid undergoes oxidation in the presence of copper chloride to form chlorine. This reaction forms the basis of Deakin's method for the preparation of chlorine, which is obsolete now. Dioxygen reacts with several organic compounds, such as hydrocarbons and carbohydrates on ignition, forming carbon dioxide and water. Now let's look at the uses of dioxygen. The main importance of dioxygen lies in its support to vital processes, such as combustion and respiration. Dioxygen mixed with carbon dioxide or helium is used for artificial respiration. It is used in the manufacture of many metals. It is used in oxyacetylene welding and metal cutting. It is used to oxidize ammonia in the manufacture of nitric acid. Oxygen cylinders are widely used in hospitals, high-altitude flying, and in mountaineering. Liquid oxygen is an important constituent of the fuel used in rockets.